Welcome to today's Explainer. We're jumping right in to completely demystify a term that honestly sounds incredibly intimidating, but is actually the hidden engine behind some of the most important medical and chemical technologies we use every single day. We're talking about chronoamperometry. By the end of our time together, you'll understand exactly how this fascinating electrochemical technique works, step by step, and you'll see firsthand how it powers modern biosensors.
Here is our quick roadmap for today. We'll start with the core concept, move into the current response, break down the Cortrell equation, look at double step and charge, and finally, wrap up with those real-world applications.
Section 1. The core concept, current over time.
Okay, before we dive into any data, let's just break down the word itself. Chrono means time, and amperometry refers to the measurement of electrical current. So quite simply, we're measuring how an electrical current changes over time in response to a sudden change in voltage. And to ground us in reality, there's absolutely no magic here, just a very precise physical setup. If you walked into a lab, you'd see a laptop recording data hooked up to a machine called a potentiostat. That's the box that tightly controls the voltage. Connected to that is a beaker of aqueous electrolyte containing our electrochemical cell. It relies on a classic 3-electrode system, a working electrode where the actual magic, our target reaction, happens, a reference electrode to keep our voltage measurements perfectly accurate, and a counter electrode just to complete the circuit. This physical hardware is the foundation for everything we're about to explore.
Section 2. The current response and the effects of stepping the voltage. So what actually happens inside that beaker when we flip the switch and start manipulating the voltage? Well, it's a brilliant showcase of cause and effect. At time zero, we dramatically step the potential from a baseline voltage, where nothing is happening, straight up to a highly reactive voltage level. We instantly create an environment where our target molecule is literally forced to react. And the moment we step that voltage, the electrical current spikes massively. But it doesn't stay there. It immediately begins this long, sweeping decay over time. Why? Because the reaction slows down as it becomes limited by how fast the target molecules can naturally diffuse, or essentially swim, through the liquid to reach the electrode. To really grasp why that current decays, we need to zoom all the way into the microscopic level right at the surface of the working electrode. Let's look at the exact moment right before we step the voltage, at time zero. What's super interesting here is the perfect uniformity. Before we turn the power on, our target reactant is perfectly and evenly distributed throughout the solution, sitting flush against the very edge of the metallic electrode surface.
But bam, the exact second we step the potential up, everything changes. The electrode instantly consumes the reactant that is directly touching its surface. The concentration right at that zero mark instantly drops to absolute zero. But just a microscopic distance away, the solution is still totally full of the reactant. This creates a massive, sharp concentration gradient. The reactant desperately wants to flow down this gradient into the empty space at the electrode, and it's this rapid flow that creates our massive initial burst of current.
Let's watch how this plays out over time. As the clock ticks forward, that zone of zero concentration slowly expands outward into the surrounding solution. We call this the diffusion layer. Because the reactant is being eaten up way faster than new molecules can swim in from the bulk of the liquid, the slope of our concentration profile just gets flatter and flatter. And a flatter slope means a weaker driving force for diffusion. Fewer molecules reacting per second means that electrical current slowly dies off over time, just like we saw on the decay graph.
But wait a second. We really need to address the elephant in the room here. Why does the current spike quite so violently in that split second we step the potential? Is it really just the rapid reaction of our target molecule, or is something else hiding in that initial burst of data? It turns out if we look closely at that sharp spike, that massive initial jump isn't solely from our target chemical reacting. Actually, it's heavily influenced by something called electrical double-layer charging. You see, the total current is really a combination of two things: the Faradaic current from our actual chemical reaction, which is what we actually care about, and a charging current, which acts almost like a zap of static electricity right on the electrode.
So what causes this non-reactive charging current? Well, when we step the voltage, the metallic electrode suddenly becomes highly charged. Instantly, oppositely charged ions and polarized water molecules in the liquid rush the electrode's surface to balance it out. They literally line up like magnets, forming a rigid, compact layer, the electrical double layer. This microscopic stampede of charged particles creates a very brief but incredibly intense burst of electrical current. It happens in a fraction of a second and then completely vanishes, leaving only the slower, diffusion-limited decay of our actual target reaction behind.
Moving on to Section 3, the control equation and how we quantify this decay. Now that we have a really solid physical understanding of why the current spikes and then sweeps downward, we are ready to quantify it. And please, don't let the math intimidate you. The Cottrell equation simply describes the exact physical decay we just witnessed. It's basically the bedrock mathematical formula of chronoamperometry. It proves mathematically that in a strictly diffusion-controlled environment, the decaying electrical current is directly proportional to the inverse square root of time.
And here is that famous equation itself. The current over time is equal to a stack of variables divided by the square root of pi and the square root of time. Now, while it might look like a bit of alphabet soup right now, this elegant little formula perfectly maps out the sweeping, curved graph we looked at earlier. It literally takes the physical chaos of millions of molecules swimming toward a piece of metal and turns it into highly predictable, incredibly precise data. Let's just methodically break down these variables, because this is where the magic really happens for analytical chemists. In the top half, we have N, the number of electrons transferred, F is Faraday's constant, A is the surface area of our working electrode, C is the bulk concentration of our target chemical, and D is the diffusion coefficient, which is basically a measure of how fast our molecule naturally swims. Now here is the absolute secret. In a controlled laboratory test, N, F, A, and D are locked-in constants. They literally do not change. Because of that, the electrical current we measure essentially acts as a direct, perfect mirror for C, the concentration of our target chemical. You measure the current, and boom, you instantly know exactly how much of your target chemical is in the sample.
Section 4. Double step in charge. Advanced techniques.
So that single step gives us incredible data. But what happens if we make the experiment just a little more complex? This is what we call reversal double-step chronoamperometry. Instead of just stepping the voltage up and leaving it there, we step it up to trigger the forward reaction, let it decay, and then violently step the voltage back down to a totally new level. This sudden drop actually reverses the reaction. It lets us probe the ultimate fate of the chemical species we just generated a few seconds prior. It's an absolutely fantastic way to study complex reaction mechanisms and see if our chemical products are stable or if they've already degraded into something else entirely.
Another totally brilliant trick is that rather than just looking at the raw current, we can mathematically integrate that current over the entire time period to calculate the total accumulated electrical charge. This specific technique is known as chronocoulometry. And why do we do this? Well, it allows us to easily separate the signal of molecules freely floating in the solution from the molecules that are stubbornly stuck, or absorbed, directly onto the electrode surface. By plotting this total charge against the square root of time, creating what's known as an Anson plot, we can precisely measure those surface-bound reactants.
Finally, Section 5. Real-world applications and how this is saving lives today.
Okay, so we've covered potentiostats, diffusion layers, and some pretty heavy equations. It's time to bridge the gap between these dry lab concepts and how this technology is actively being used in our everyday lives. What is the ultimate so what connection here? Beyond helping scientists calculate electrode surface areas and molecular diffusion in a lab, chronoamperometry is the exact science behind massive healthcare breakthroughs. Take blood glucose test strips. The millions of test strips diabetics use every single day to monitor their blood sugar rely directly on this technology. A drop of blood reacts with an enzyme on the strip, it liberates a product, the device applies a potential step, and the resulting current decay, following the exact Cottrell equation we just learned, tells the device precisely what the glucose concentration is in a matter of seconds. It is literally high-level electrochemistry fitting right in the palm of your hand.
And that brings us to the absolute frontier of today's science. We already use simple potential steps for glucose monitors, but researchers are now utilizing repetitive pulsing and complex double-step techniques for real-time in vivo bioanalysis right inside the human body. So I leave you with this final thought. If the simple step of a voltage can already manage a global disease like diabetes, how might manipulating these microscopic electrical graphs unlock the very next generation of life-saving biosensors? The answers are quite literally hiding in the current. Thanks so much for joining me for this explainer, and keep questioning the science around you.